Continuing on with colligative properties, we now are going to talk about osmotic pressure. So we say we have the following setup here. We have pure water on the left, and we have some solution on the right, which has some solute in some dilute quantity. What's going to happen if we have a rigid semi-permeable membrane in the middle here? Semi-permeable meaning that water is allowed to flow back and forth across this membrane, but the solute cannot flow back and forth, so only water can flow. What will happen is that over time, the water, through osmosis, which is the name of this process, will flow from the region of pure water into the solution. And the result will be we'll have less water, pure water, on the left side, and we'll have a diluted solution on the right where the water has flown over and diluted the solution. And the result is we have this flow occurs until you reach a difference in height such that the difference in pressure caused by this varying height in these water columns reaches a value called the osmotic pressure, which we're going to indicate by capital pi. So what we want to know is, depending on what the concentration of our solute is here, how much water is going to flow through this semi-permeable membrane by osmosis, and what osmotic pressure will it reach when it reaches equilibrium. Okay, so this is a job for chemical potentials. So what we have here on the left is pure water. So we have mu star 1, the chemical potential of our pure solvent, pure water, at a given temperature and pressure. That is equal to the chemical potential of water in our solution at that given temperature, that pressure plus the osmotic pressure, because the pressure over here is atmospheric. The pressure over here is the atmospheric pressure plus osmotic pressure, and at the given activity of water, which occurs over here. So chemical potential of water in the solution versus at the higher pressure versus chemical potential of pure water at atmospheric pressure. Okay, so we can deal with the chemical potential caused by the activity of water being less than 1, the mole fraction being less than 1. We have mu1 star of T and P equals mu1 of the solution at T and P plus pi plus RT log activity of the water in solution. So that comes from our expression for the chemical potential in a solution. So now we just need to figure out the difference in chemical potential in the water at the two different pressures. P. Okay, so I'm going to move over this chemical potential of water at the two different pressures here. So we're going to have our chemical potential of water in solution at high pressure minus chemical potential of water at low pressure plus RT log activity equals 0. So I just move this over. So we're going to try to figure out what this quantity here is, what this difference in water's chemical potential at two different pressures is. So first thing we can utilize the fact that the partial derivative of the activity of pure water, or partial derivative of the chemical potential of pure water with respect to pressure, because the pressure is changing, at constant temperature, it's at T in both cases, is equal to the molar volume of pure water. So this is just the molar Gibbs energy. The derivative of Gibbs energy with respect to pressure is volume, so the derivative of molar Gibbs energy with respect to pressure is molar volume. So we can use that fact when we do this following integral. We're going to have that this quantity is the integral from P to P plus pi of partial derivative of chemical potential of pure water with respect to pressure at the given temperature, integrated with respect to pressure. So this, as we've shown here, this partial derivative is the molar volume. So we have integral from P to P plus pi of the molar volume of water, integrated with respect to pressure. So the molar volume is not a function of pressure here. We're going to assume that that is independent of pressure for a liquid, which is a pretty good assumption. It doesn't change very much at all for water. It's pretty insensitive to pressure. So that means we're just integrating dP to P from P to P plus pi, which is just going to give us pi. So the result of this integral is the molar volume of water times pi. Okay, so going back to our top expression here, that gives us that the difference in these two, we had pi times molar volume of water is equal to minus RT times log of the activity of water. And once again, our favorite Taylor series is going to strike and rear its ugly head. The log of the activity of water, when its mole fraction is approximately 1, is approximately the mole fraction of water, which is equal to log of 1 minus mole fraction of the solute, as we've seen in 2 videos now. And this first order Taylor series expanded around chi2 equals 0 is minus chi2. So we've done this in 2 previous videos now explaining why. And we know that our mole fraction here, chi2, is equal to number of moles of solute divided by number of moles of water plus solute. But if N2 is much greater, is much smaller than N1, so it's a dilute solution, then this is approximately N2 over N1, because N1 plus N2 is approximately equal to N1 if N1 is much greater. Okay, so we can substitute in that fact up here, and when we substitute that in, what we're going to end up getting, so we're going to have pi times molar volume of water is going to be equal to RT times N2 over N1. All right. And then we can rearrange this equation. We're going to have pi equals, then we're going to have N2 RT over V bar 1 N1, which if we have the molar volume of water times the number of moles of water, well, molar anything times number of moles is just that thing, so molar volume times number of moles is just volume. So we have N over N2 over V times RT here, but N2 divided by volume, so we have number of moles of solute divided by volume of solution. That is just the definition of molarity. So what we have indeed found is consistent with what we claimed a few videos ago, and that the colligative property of osmotic pressure is just going to be the molarity of our solute times gas constant times temperature. So the C, again, is the molarity of the solute, and that is in units of moles per liter. Okay, so indeed the main assumption that we had here is that the activity of the water was approximately equal to mole fraction, which was approximately equal to the Taylor series here for dilute solution. That Taylor series working for dilute solution. So for over a range of small molarities, so for a dilute solution of whatever this solute is here, the osmotic pressure is going to be directly proportional to its molarity, and that is irrespective of what kind of particle is this solute.